So this is the start of our notes in biochemistry. I told you in class that I want to do a lot of things online this year so we can cover some of those easy things, some of those review things outside of class and work on the hard stuff in class. So we're going to start here with chapter 1, Principles and Tools of Science. And the first thing we need to cover is this idea of hypothesis, theory, and law. So this is stuff you've done every year in a science class. It shouldn't be new. But just to go through definitions again and make sure we understand this, a hypothesis is a statement meant to explain a set of data, right? You do this all the time. You come up with an idea, something that you believe is true, right, that will work, and you test it, right? So when you show up to school and you see your friend doesn't look super happy, kind of maybe grumpy, kind of moping around, and you're just collecting data from your environment. You're seeing that they just don't look normal. Maybe they're having a bad day. And that's a hypothesis right away. You can test that hypothesis just by saying hi. Right? If they snap your head off, then they're probably having a bad day. And you were probably right, but maybe they aren't having a bad day. Maybe they just, I don't know, something was going through their head at that time. So you always got to test your hypothesis to make sure that it's true. But this is something that we do all the time. Obviously, in science, it's going to be a little bit more technical than that, but you would know what a hypothesis is because you've done it over and over again. Whereas, again, that theory is the same thing as a hypothesis. It just has a lot more support, right? Hypotheses turn into theories, right? Sometimes it's more than one hypothesis that turns into a theory to explain how a certain phenomena works, right? And then finally you have that law, but that's where some people get confused, right? A law is just a generalization based on consistent results, right? A law is just when I throw a marker up in the air, what's it going to do? It's going to fall, right? So it's actually completely different than the hypothesis and the theory, and that's the main takeaway for this that I want to make sure we understand. Right? A hypothesis absolutely can turn into a theory. Because the only difference is that theory has tons and tons of support, and we absolutely think that that's true based on the evidence that we have. Now, because this is science, if new evidence came about that contradicts that theory, we definitely would change it, right? We're never set in stone, right? There's no such thing as absolute. But what some people get confused about is they think, oh, okay, next step up, law sounds like a way better name than a theory, right? Because when we use theory in our normal English usage, that sometimes doesn't hold very much strength, right? Sometimes we think, oh, that's just an idea, right? It's an untested idea even. But no, in science, a theory is a super redundantly tested idea, right? There is so much evidence to support that there's no way based on current evidence that is wrong, right? But theories do not turn into laws. Just because a law sounds better than a theory doesn't mean that that's the way it works, right? The law existed from the beginning. Excuse me. The law of gravity came about long before the theory to explain how gravity works, right? The law is just telling you that when you drop your marker or your pencil, it's going to fall. When you let go of it from a height, it's going to fall, right? And that happens over and over again. It doesn't matter if you're here, right, in Europe, on the top of Mount Everest, it's always going to happen, right? So gravity exists, right? We know that this phenomena exists, but why does it do that, right? The theory is what actually explains how that phenomena works, why it happens the way that it does, right? We know that the mass of the Earth pulls on us and keeps us on the Earth, on the surface of the Earth, right? Two masses are attracted to each other through gravity, and there's an equation in that theory, right? Usually there are models, which in science talk actually typically is like a math equation, right? Not necessarily just a diorama or something like that. But there are models that can actually explain exactly how these bodies large masses move around each other and why this thing works, right? So we see all these massive objects in our solar system, in our galaxy, and we can actually explain using math exactly where they go and why they go that way, right? That's what the theory is. The law is just that, well, if you drop your pencil, it's going to hit the ground, right? So law is actually something that's very simple, and it was always there. The law was what we were trying to explain to begin with. The law came before the hypothesis, in reality. So just understand the difference, and we should be okay on that. We're not really going to go too in depth on that in class or anything crazy, but that's just a common misconception, so I want to make sure we clear that up. So your scientific method, first step, every time, gather as much data as you can. Okay? No matter how great and original you think you are, there is a chance that somebody's probably done this before. You should always look, right? There are millions of experiments on file in journals, scientific journals, and just because you think this is a brand new idea doesn't mean that it is. So you're always looking, sifting through all that data that exists to see if somebody's done it before. There's no real reason to reinvent the wheel, but if you do come up with that unique idea and you have enough data to have an idea of maybe how this works, right, then you would definitely make a hypothesis. And then definitely test that hypothesis. The problem with science as a career, right, if you're going to work in a lab or if you're going to, whatever you want to do, is that really there's only two results after that testing, right? You're either going to accept your hypothesis, which would be great and wonderful, or you're going to reject that hypothesis. And you kind of have to get used to the latter, right? More often than not, right, scientists are rejecting their hypotheses. They come across new data that tells them, nope, that's not really how that worked. So they're just remaking those hypotheses and testing all over again, and they really get stuck in this little feedback loop here, probably 99.9+% of the time, right? So you have to get really, really used to failure if you're going to go into that kind of career, right? Because most of the time, it's not going to work the way you thought it was going to work. And even sometimes when you can accept it, maybe that less than 0.1% of the time, not greater than, less than, even when you do accept it, sometimes somebody else tries to replicate that result and blows it up. It magically worked for you, but it doesn't work for anybody else. So you always have to test those things and retest those things multiple times to make sure that it's actually what you think is supposed to happen. Because a lot of times you get lucky, and it doesn't really matter if you get lucky. If somebody else can't do it, it's not true. So a lot of time you get stuck in that reject, remake, reform that hypothesis. But every time you test a hypothesis, you get more data. So you really almost come back here, and the more data you have, the more likely it is that you can actually figure things out. So it's not a bad thing. It's just part of the deal. You got to get used to failure. Otherwise, we jump right into measurements and units. We were measuring things that first day in class, so this shouldn't be anything new to you either. But just to overview these things, numerical information observed are measurements, right? It's a description of a physical property, right? Physical properties would include length, volume, mass, temperature, time, things that you'd be familiar with. They're always going to have a number and a unit, so when you guys measured that length, not only were you supposed to write 22.65 centimeters, or excuse me, 22.65, but you're also supposed to put a centimeter on that, so make sure you always have a unit, or else you have no idea what it is, nor do you know what size it is, right? When I write centimeter, you automatically know that I'm talking about a length, right? You know what physical property I'm describing. But you also know the size of that measurement, because a centimeter is a little bit different than a kilometer, right? That same value would be a little bit different as a kilometer. It'd be like this many kilometers, but right, the size is definitely going to be a little bit important in this. Right, there's a big difference between a kilometer and a centimeter. Right, 22 kilometers is a long distance. 22 centimeters a very, very, very short distance. So those units, not only do they tell you what you're measuring, but they also tell you how big that thing that you measured was. Okay, as far as those units are concerned, you have a table in your notes, right? All I'm really going to focus on in these notes is the first and third columns, the measurement, and the metric columns. I'm probably going to avoid that English column altogether, but so just to reiterate, and also just using symbols to make sure we know what they are. Right, a little m is mass, lowercase l is length, a capital V is volume, because a lowercase v is actually velocity. Little t is time, big T is temperature. So make sure you can straighten those things out. Eventually you start having to deal with a lot of those things in the same equation, and it can get kind of confusing and daunting. It is daunting to start, but you get used to it. So I got mass, length, volume, time, temperature, and I'm just going to go over the metric things for those, right? So mass is supposed to be grams, right? We have a balance in the back of the room that you can obtain the mass of any object with. Basically, that mass, though, does not include the force of the gravity, right? So when you use that triple beam balance in physical science, right, you're comparing two masses together, right? That takes gravity out of the equation because it really doesn't matter because the pull's the same on both sides. But mass is measured in grams in the metric system, right? Length is measured in meters, right? You have different sizes of meters and grams, obviously. You have kilometers, you have centimeters, like we just talked about a second ago. But meters is that base unit. Volume is going to be liters as a base unit. Time actually is universal. It's kind of hard to screw that up, right? When we have those 24-hour days and we break them up into seconds, that's based on how fast our Earth spins, not anything else. So it's kind of hard to get that screwed up from one system to the next. So we've pretty much always used the same time units. But then temperature, right? We're actually going to use two different temperatures in class. Metric is supposed to be degrees Celsius, but we're also going to talk about Kelvin later, right? And Kelvin is that SI system. And I'll talk to you about that later. Basically, the gist, though, right now, right? Celsius, we like having 0 degrees being freezing and 100 degrees being boiling, right? And that's what the Celsius system is built off of. So it works really well for us. It's useful. Those numbers are nice and clean most of the time. Kelvin exists because absolute zero exists, right? So we're going to do equations later, and we have to worry about that lowest possible temperature because we can't really have negative symbols, signs in equations and not get things all screwed up. So we'll talk about Kelvin a little bit later, but we're going to use Celsius most of the time when we're measuring, right? But we might have to convert to Kelvin so that we can do an equation with it, with that measurement. The one major thing that I might point out is a little bit of a redundancy here. If I have a little m, it's mass, right? But it's only mass if it's in an equation. If I got an equation like force equals mass times acceleration that you've probably heard of before, right? That little m represents a mass, right? But over here, 22.5 meters, that's a unit, that's a different thing, right? So you kind of have to understand the difference between something that's a unit versus something that's in an equation, a symbol that's in an equation that represents that physical property, mass, right? And in fact, this acceleration right here has a compound unit, right? For if we were using this to measure our weight on this planet, right? the acceleration due to gravity is 9.8 meters per second squared, so it can kind of be confusing. I got a meter here, I got a little m here, which one's which, right? So if it's attached to a number, it means meter. If it's part of an equation, it means mass. You just kind of have to get used to it. And I actually touched on this a little bit already, right? Mass is the measurement of matter. How much stuff is there? That should always be constant, right? When you use a balance, you are obtaining a mass. You take gravity out of the equation, right? Weight is when you do account for that gravitational pull. So those two terms are actually different from each other. They can be interchangeable at times because, most of the time you experience 9.8 meters per second as acceleration due to gravity. So one mass versus another, they end up having a similar weight, right? But make sure you just understand the difference. Again, real example. You got our planet, you got the moon, right? I would weigh 100 kilograms whether I was standing on one or the other. I would have a mass of 100 kilograms, no matter which one I'm standing on. I'm probably never going to stand on the moon, but if I did, I'd still be 100 kilograms. I can't make the stuff that's in me just disappear just like that. It's still there. So I'd be 100 kilograms either way. But remember, if I take that mass, 100 kilograms times an acceleration, that would give me a force, which is a weight, right? Right? That equation we just talked about a second ago, force equals mass times acceleration. Right? If I multiply these two things, I get an answer of 980 and a new unit that you don't know about, newtons, right? My weight, using newtons instead of pounds, is 980, right? Whereas on the moon, I'd still be 100 kilograms, but I'd take it times 1.6 meters per second squared, and I'd only have a weight of 160 newtons, right? Which is roughly 16% of what my original weight was. I'd be a lot lighter if I was standing on the moon, but I'd be a heck of a lot heavier if I was standing on Jupiter somehow. Kind of hard to do that because Jupiter is a gaseous planet, but if I could stand on the surface without just crashing down to the center and being crushed to death, I'd have a very large mass there. I'd have a very large weight, Okay, so that should be good for now, for this first video.